Hey everyone, and welcome back. Today we're going really far out there. We're going to be talking about NASA and their plan to launch an artificial star.
Wow, an artificial star. That's pretty ambitious.
It is, and we always try to cover the most interesting stuff here. So we've got this article from Caltech. It's all about this mission called Landolt. And I guess the first thing is, what is the point of launching a fake star?
Well, if you think about it, to really understand space, we need to be able to measure things out there. And one of the most important things to measure is the brightness of stars.
Okay, so we're measuring brightness. How does a fake star, how does that help?
So by sending this artificial star up, it'll shine with, a very specific brightness. It's like a cosmic yardstick.
Like that cosmic yardstick.
Yeah, it lets us calibrate telescopes really, really accurately so that then when we measure a real star, even one that's super far away, we'll know exactly how bright it is.
A reference point. So that means that we can then learn more about the real stars.
Exactly, yeah. We can figure out how big it is, its temperature, how old it is, what it's made of, all kinds of stuff.
That's amazing. I noticed this article also mentions exoplanets. How does measuring a star's brightness, how is that going to help us learn about planets around other stars?
Well, you have to think about the star and the planets around it as, a system.
Yeah.
So knowing more about the star can tell us a lot about the planets. Think about it. A super bright and hot star is going to have a really different effect on the planets near it than one that's, smaller and cooler.
Right, yeah.
And so if we can really nail down how bright a star is, then we can create a much better picture of what the planets orbiting it are like. We might even be able to find planets that could support life.
Whoa, wait, really? We could use this artificial star to find out if there are other planets out there that, that maybe have aliens on them.
Maybe, yeah. If we can look at the light passing through a planet's atmosphere, we can start to figure out what that atmosphere is made of, and that might tell us if it could, have life on it.
Okay, I think I get that we're analyzing light, but how do we actually do that? How can you tell what a planet's atmosphere is made of just by looking at light?
Well, when a planet passes in front of its star, from how we see it here on Earth, some of the star's light passes through the planet's atmosphere.
Okay.
It's like if you were shining a flashlight through a colored sheet of paper.
So it changes.
Yeah, the light changes color. And so we can, by carefully looking at that light, we can figure out what that atmosphere is made of. If we see things like, water or oxygen or methane, those could be signs that the planet might be able to support life.
So then the better we can measure that light, the more we can learn about the planet.
Yeah, that's where this artificial star comes in. Because it's like it gives us a perfect baseline so we can measure the real star much better. And that means we can also measure the light from the planet's atmosphere way better, too.
We keep talking about this 10 times better accuracy. What does that actually mean? Like, how much better is that, really?
It's a lot. It's like, even with our best telescopes, when we measure the brightness of a star, there's still there's still a margin of error. It's like if you're using a ruler but the markings are blurry.
Okay, yeah.
This Landolt mission is like getting rid of all that blur. It's a crystal clear measurement.
High definition instead of, standard def.
Exactly, yeah. And that makes a huge difference. It means we can learn way more about these stars, and it might even help us figure out dark energy.
Hold on, dark energy. I thought we were talking about planets. Now we're all the way out to dark energy. What is dark energy? I've heard that term, but I'm not really sure I get it.
So we know that the universe is expanding, but, and this is the weird part, it's expanding faster and faster.
Really?
Yeah, like it's accelerating. And based on what we know about gravity, it shouldn't be doing that. So scientists think there must be something else out there that we can't see that's, making it speed up. They call that dark energy.
Okay, so that makes sense. But how can measuring starlight, how can that tell us about dark energy?
We can look at these things called supernovae. They're basically when stars explode. And we can use those to measure distances across the universe.
So they're like cosmic mile markers.
Yeah, exactly. But here's the thing. The better we can measure how bright those supernovae are, the more we know about how fast the universe is expanding. And that can tell us more about this dark energy.
Wow, so this artificial star, it might help us solve one of the biggest mysteries in, all of space.
It could. And that's what makes this mission so cool. It's not just about, measuring things better. It's about really trying to understand how the universe works.
Okay, I'm definitely on board with this. So where is this artificial star going?
It's going to be about 22,000 miles above Earth.
That's not that far.
It's actually a very strategic location. It'll be fixed over the United States.
Oh, wow. Why there?
It's so that our telescopes here can see it all the time, and it'll stay in the same spot in the sky because it's going to move at the same speed the Earth rotates.
So it'll just be like a constant beacon up there.
Yep, always there, helping us unlock the secrets of the universe.
I love it. And who is making this happen?
Well, the mission is being led by George Mason University, and there are partners like Caltech and the National Institute of Standards and Technology, and it's named after astronomer Arlo Landolt, who spent his career making, these super detailed catalogs of stars.
It's pretty amazing that one well-calibrated light source could change how we look at everything out there in the universe.
Yeah, it's really quite remarkable.
It is. And there's a lot more to talk about with this. So we're going to take a break, and when we come back, we'll dig even deeper into the potential of this game-changing mission. And we're back. Man, this artificial star thing has really got me thinking.
Yeah, it's a big deal for sure. A real testament to how much progress we've made, both with technology and just like how we think about the universe. And honoring Landolt's work too. That's pretty cool.
Yeah. Yeah, it is. Okay, so we've talked about what it is and why it matters, but I want to know, how does it work? How does this fake star make our measurements, 10 times better?
Well, it's all about having something that is accurate to compare everything to. Like, imagine you're trying to measure a table, but your ruler is all bent out of shape and the markings are faded. You're not going to get a good measurement.
Right.
But if you have a really good ruler, one that's perfectly straight and the markings are clear, well, then you're golden. That's basically what this artificial star is. It's like a perfect ruler for space.
A perfect ruler. Okay. But why do we have to launch it into space? Why not just, build this perfect star here on Earth?
Because of Earth's atmosphere. Our atmosphere, it does weird things to light. It distorts it. It's like trying to look through a glass of water.
Okay, so the atmosphere gets in the way.
Yeah. So by putting this artificial star up in space above the atmosphere, it's like we're getting a perfect view. And because it's going to stay in the same spot relative to us here on Earth, there's no distortion. It's just a constant signal.
Got it. So constant signal, perfect reference point, means we can calibrate our telescopes really well and then measure those real stars, even the ones that are super far away, much more accurately.
Exactly, yeah. And that has implications for everything. Like, we'll understand individual stars better, but also, bigger things like how the universe is evolving.
Okay, I get all that, but I'm still a little hazy on the dark energy stuff. How can we learn about something as wild as the force that's expanding the universe by doing this?
It's about those standard candles we talked about, the supernovae.
Right.
So we use them to measure how far away things are in space, and the better we can measure them, the more we know about how quickly the universe is expanding. And that gives us information about dark energy.
So it's like, we know the universe is expanding, but this helps us figure out exactly how fast.
Yeah. It's like, imagine you're driving down the highway and you want to know how fast you're going. So you look at the mile markers.
Okay.
If you know how long it takes you to get from one to the next, you know your speed. But if those mile markers are wrong, you're going to get the wrong speed.
I see.
So the supernovae are like our mile markers. And by making sure they're accurate, we can figure out the speed of the universe, so to speak.
Man, it's incredible that measuring light can tell us so much about the universe. Like, we're literally learning about the biggest stuff out there by looking at something so small.
It's pretty amazing, right? It really shows you how, everything's connected in the universe.
Yeah. Okay, so we talked about dark energy, but I also want to know more about, regular stars. What can this mission teach us about them?
Well, for one, it'll help us learn a lot more about how stars evolve, how they're born, how they live their lives, and how they die.
So we can make a better timeline of a star's life.
Yeah, exactly. And that tells us a lot about, how galaxies form and where all the different elements come from.
Well, elements like the stuff that we're made of.
Yeah, a lot of the elements that make up our bodies, they were actually created inside stars. And when those stars die, they release those elements out into space.
Whoa, so we're literally made of star dust.
In a way, yeah.
That's wild. So this mission, it can, trace those elements back to their source.
Yeah, it can help us understand, the whole cycle of matter in the universe.
Wow, this is really blowing my mind.
It's pretty incredible stuff. And the coolest thing is, we're just scratching the surface. There's so much more that we can learn.
I can't wait to find out what it is. We're back and ready to keep exploring. This whole artificial star thing, it's pretty mind-blowing.
Yeah, it really is. We've talked about, stars and dark energy, but I think the biggest thing, for me at least, is what this could mean for finding life on other planets.
Yeah, that's what I'm most excited about, too.
Imagine being able to analyze the air on those planets, but with, 10 times better accuracy. That could be huge.
Like we could finally find proof that we're not alone in the universe.
We might, yeah. I mean, we might be able to find those, those chemical fingerprints that say, hey, there's life here.
Like oxygen, right? Or
Yep.
methane, stuff like that.
Exactly. Right now, our instruments, they're just not good enough to see those things. But with this Landolt mission, it's like we're getting a brand new, super powerful, telescope. We could see things we never could before.
It's like getting a much stronger pair of glasses, right?
Yeah, exactly. We'll be able to really see these planets clearly for the first time. And who knows what we'll find.
I can't even imagine. Maybe planets just like Earth, or maybe planets that are, totally unlike anything we've ever seen before.
Exactly. It's a whole new world of possibilities, literally.
It's really exciting. Earlier you were talking about that cosmic distance ladder. I'm curious, how does this mission, how does it help us measure distances better in space?
Oh, that's a good question. Yeah, so the cosmic distance ladder, it's basically it's like a bunch of different ways that we measure how far away things are in the universe.
Okay, and each step on the ladder uses like different methods, right?
Yeah. Yeah. For nearby stars, we use a method called parallax.
Parallax, isn't that kind of like how our eyes work?
Yeah, it's kind of like that. We look at a star from two different points in Earth's orbit, and we measure how much it seems to shift.
And that tells us how far away it is?
Yep, pretty clever, huh?
It is, yeah. But that only works for stars that are relatively close, right?
Right. For stuff that's further away, we use other methods, like we can look at Cepheid variable stars and Type Ia supernovae.
Oh, those are those standard candles, right?
Yeah.
The mile markers we talked about before.
Yeah, those are the ones.
Okay, so how does Landolt improve those measurements?
It makes them more accurate. Like imagine you're trying to measure the length of a football field, but your tape measure is, it's old and stretched out.
Your measurement is going to be way off.
Yeah. But if you have a brand new tape measure, one that you know is accurate, then you're going to get a much better measurement.
So Landolt is like that brand new, super accurate tape measure for the universe.
Exactly. It lets us measure distances, much more precisely. And that's important for all sorts of things, like figuring out how galaxies are arranged and even how the universe is changing over time.
Man, it's incredible to think about this one mission could change so much about what we know about space.
It really could. It's a huge step forward in our understanding of the universe, and it's a reminder that, we humans we're curious creatures. We always want to know more.
I think that's a great place to wrap things up. We've covered a lot today, from the specifics of this mission to the big questions about, life and the universe.
It's been a great discussion. I always love talking about this stuff.
Me too. And to our listeners, thanks for joining us on this deep dive into the incredible world of astronomy. Keep looking up at the stars and never stop wondering about the mysteries of the universe. We'll see you next time.